everybody, welcome to our new class, and this class we're going to talk about resistors. So what is the concept of resistor? So first of all, let's say that no matter what you have learned so far, this topic would be irrelevant, like a fresh start, okay? And the concept we're going to talk today is we learned so far about capacitors. Capacitor is the way to accumulate energy, or about a battery, okay? A given energy that we have, a potential difference, right? So the really interesting thing is not to have energy, is actually to waste the energy, to use it, to have fun with the energy, like money. You don't want to accumulate money, you want to spend it to do stuff with the money, right? So this is the concept about today. So resistors is the way for us to present how the energy leak from the circuit, from the problem, run away, okay? Perfect. So anybody here have any collection of something? I have a collection of coins, okay? So if you want to go to do some crazy thing with your collection, you can go to Guinness record, okay? So the first question is about a tower. Here it is, a tower that made out of coins, a lot of coins. You see that? And the kid that collect the coins want to break the record of the highest record coin tower in the world, and he called Guinness to come and measure the height of the coins, and it's a big problem. Why? Because if they want to stretch some line from there to there is a wind, okay, interfere the measurement. If they want to measure how much coins it have, he didn't put it on a weight device. So what's the option that they have? So Guinness said, okay, no problem, don't worry about that. What we're gonna do, we're gonna connect the lower coin to a circuit with the battery. Here's the battery. Okay, let's do a better one, this, and we can forget you. Here it is. They connect this part and connect this part, okay? And they know what is the resistivity, okay? This is a new property, okay? Resistivity, I know rho used till now for charge density, for volume problem, but it's also a resistivity, which means how much something resists to current. We're going to talk about it. So the resistivity is a function of space, of z. So this is going to be z, right? And it's equal to some constant divided by the length of the resistor, this thing, multiply by z to the 5 pi a squared. Come in really fast. Hello. Okay. I'm going to repeat the problem for you, but sit down. Okay, good. And what I want to ask you, the first question, is what is the resistance of only one coin? This thing. Only one coin resistance. Okay? So I'm going to repeat the question. We have a tower built up of coins, and we want to measure what is the length of this tower. We cannot do it in other ways, but we can do it using electrostatics effects, using connecting this coin and this coin to a battery. We have this property, which is not the charge density. This is the resistivity of this element. This measures how much each element actually resists current going inside. Current is the move of charge. Okay, perfect. So if we're going to look at one coin, this is going to be the first question. What is the resistance of one coin? Okay, one coin of the tower. So one coin is actually looking like this, right? This is one coin, and the formula for resistance is going like that. R, and I have a funny way to remember it, okay? The funny way is resistance is something that makes you sad, right? You don't want to resist. So I do a sad smiley, that's my method, and then I fix it to be the real formula. This is A. Here we have denominator and denominator. This is rho, and this is L. Okay, this is my method, but the formula is rho, this thing, multiplied by the length that the current go through the resistor, divided by A, the area that the current actually seeing. Here we have a current, electrical current, which mean positive charge that actually moving at the direction, right? So what is the resistance of this thing? I'm going to move to the other board. Cameraman, I'm going to move to that. You know what? Don't forget about it. I'm going to do it here. So first of all, we're going to talk about dr. Why dr? Because let's say that whole of this building is actually the big resistance. And we're just going to talk about one coin, so I note it by dr. So what is the length, if this is the positive charge, that try to go through the coin, yeah? So we need to understand what each one of them. For example, what is the area they see? If the coin have radius of A, which is known, right? Yes, so this is going to be pi A square. And the thing is that each time you're going to face a resistor problem, you need to understand each of the parameters, okay? What is the distance that the charge we need to go through? What is distance? In what direction it is? Is Z, but it's a small unit, right? It's a small coin, right? So this is going to be dz, exactly, good. And now we are left with the resistivity, and the resistivity is given. For each Z, I know what is the resistance of the coins. Okay, so I just can plug it in. So this is given. It's rho, which is a constant. This is not working. Let's do this, the red one. Okay, so this is rho, is given, constant, Z to the 5, L to the 5, pi A squared. Good. Okay, so we're just gonna rearrange this, right? And we're gonna have our solution, right? That's all. That's the solution for what is the resistance for only one small coin dz. Okay, I'm going to this board, and now I want to ask you, how does all these coins are connected to each other, right? We have two ways how the coins, resistors connected. We have two ways to connect stuff, right? The one way is series, exactly. Series actually mean that we have one of the terminal of the battery touching a resistor. And this resistor touching the terminal, this one touching the other resistor. And this one touching another resistor, and it goes so far until the last one, which is touching the battery. What you have here is a bunch of resistors that fighting who gonna get the voltage, right? Here you have total voltage difference V node, for example. So each one of them gonna get some of it. And what is the other method that we have? Parallel, right? And parallel is exactly the opposite. It said you have a battery, here's the battery, this terminal, you have a battery, and this terminal connected to a resistor. Here it is, a resistor. So what is the voltage on this resistor? The potential here versus the potential here, right? Minus. So it's V node. And this resistor? The same. And this resistor? The same. And this resistor? The same. So everybody enjoy the voltage. Here everybody feel like a king. I got all the potential. Okay? Here they're gonna fight about it. Who's gonna get the more? Okay? Good. And so in our case, what is the configuration? Do you have any idea? Let's check it. Okay, so we have the battery. Here's the battery. And it's touching the first coin. Touching the first coin. The second coin, touching what? It's touching the first coin from above and down below the next one. The next one. And this go far until the last coin, which touching the terminal. So which method do we have? Series. We have the series method, right? I just flip it around, but it's the series method, okay? Good. So another thing that I didn't mention, I want to go here. The formula for resistance, in general, it's the material property, how much I resist to flow of charge coming through me, multiplied by the distance they need to go divided by the area. And when I see this thing, it reminds me driving a car. Okay, instead of charge, think about a car. This is a car, right? Hop, hop. This is a car, okay? So if you want to go somewhere, okay? First of all, if it's a long way, you would resist going that way, right? Going from here to Elat, it's a huge distance compared here to the next door, right? With the car. So this is this part, okay? Going a long distance, make resistance. If you had a lot of places to go in the road, this way, this way, this way, this way, if something happened, traffic or stuff like that, you're gonna be safe, right? You can move to the other one, okay? This is saving you. So this actually decrease resistance, okay? And what is rho? Rho is actually the material property. Which road you wanna drive? You wanna drive Tel Aviv in the morning, which gonna be really, really hard, yeah, you know, many people, many cars, or you wanna be, I don't know, in Hadera at night, which is, there's nobody there, dead city, right? So this actually, a method to remember what is the formula. Another one, more intuitive, related to cars, okay, not charge, perfect. So the next stuff I wanna ask you, okay, Yoron, there's a lot of coins, okay, there's DR here, right? A lot of resistors. But what is the equivalent resistor? Okay, what do I mean by saying equivalent resistor? If we're going to take all these tower of coins outside and put only one resistor, which resistor it's going to be that's going to give the same results, the same effect as the whole tower? So the next question is, what is, okay, let's do it here, okay? So the next question is, what is R total? Okay, the equivalent one, okay? And a good method to remember it is R total in case of connecting in series is just sum up all the resistors. What we had in capacitors? It was another one, right? So in capacitor it was the opposite one to the power to the minus one. So if you want to connect capacitor versus resistor, just remember they are the opposite. Okay? A good way to remember it. Clear? Yes? The opposite from capacitors. Okay? And you can see that actually L, why in resistor it's happening? Because you see that it's like an effective long resistance. You see it? That's what actually happened. Yeah, in a capacitor what we had, this was capacitance, right? For this kind of capacitors, right? So you see L is below, right? Not up, and A, they're opposite, you see? And this is the material property. They're like similar properties. This is how much charge I can accumulate, that how much charge I don't letting go through me. Okay, this is resistance. Nice. So let's calculate it for us. Okay, I'm gonna clean this. So in our case, cameraman, in our case, we know the resistance, right? R total equal to the sum of all the small resistance that we have. And since we summary a really small value, really small changes in dz, so I can actually change this to an integral, right? Integral of dr. And dri is this term, which is, as we remember, this term. Rho 0, L to the 5 pi a squared multiplied by z to the 5 dz. So what is the integral boundaries? Because of this dz, it's like asking where in space the coins are actually placed. So they start at z equals 0, right? And finish at height L, right? This thing is a constant, which you can drag outside of the integral. So we're actually solving this integral.
Is it pi a squared or pi squared?
Pi a squared, yes.
Yeah, but don't we have another component in there?
You are right, because we have this pi a squared, right? So this I think is squared, right?
Yes.
Yes, okay. I think there is a mistake here. Let me check that, okay? But for now, let's forget about it, okay? Sorry for that. Let me validate that. Sorry. In the resistivity, we didn't have this term. Okay, we are all fine. Sorry for that. At the beginning of the video, I wrote resistivity wrong. It's without this. Okay? Okay, it also makes sense it's without this because this constant have the same unit of resistivity and this one doesn't have any units. Z to the 5 divided by L to the 5. Okay, so sorry about that. Didn't mean to do it. So we're actually fine. Okay, sorry for that. Okay, so this constant actually can be dragged outside. Rho node L pi a square. If we're going to solve this integral, it's going to be raised to the power of 6 and divided by 6, right? And here we have L to the 5, right? So we end up here just with L over 6, right? So this is, let's write it.
The power of 6, no?
Power of 6, yes. This cancel with this, right? And we end up to have this term. Perfect. Okay. So this is the resistance, how much this tower resists to current go inside. How we can measure the current that we have here inside? We can put a smart device, which called ampere meter. Let's put here. This is just a device that tells us what is the current. It's called ampere meter. The unit of current is ampere, and it's a short just for charge, coulomb per second, okay? Like how much charges, I'm the selector in the club, and there's a positive charge, 1, 2, 3, 1 second end, this is the amount of current that I have, okay? This is the units. How much charge pass in 1 second through some place, okay? Perfect. So this can give us the current, and current we signify it by the letter I, okay? And now I want to give you the formula that relate voltage, current, and resistors. So I'm going to this board, okay? So the real question I want to ask you is what is the length of the tower? Yeah, that's what we actually want to check from the beginning. L equal to this, right? And I'm going to give you an equation. This is the equation. V equal I R. Can you read the sound of this equation? V I R. How it sounds like? Vir, right? So I like to think about it as beer. Okay, this is the equation, and the equation actually really explains well the concept of electricity. Okay, so actually, if we have a beer, right? Let's have it flip upside down. Here we have some different potential, right? Gravitational potential, but think about it as a voltage, right? Okay, here outside of the beer, there's gonna be some current or flow, right? Current or flow, and if it's gonna leak or really going a massive flow, it's dependent on the resistance. How much resistance do I have? So the concept of beer actually explain it really well, okay? So this is the method to remember that. Okay, so and another thing I want you to see in the equation is what we actually have. We have some energy, and we want to use this energy, I, okay, to have a current, to move electrons, to move charge, okay? And can we do it? Depends on R. This is the concept of R, okay? And this is not always gonna hold, okay? In our class, this is hold, okay? But think about it that as temperature increase, the material change, in geometry change, you know, just learning in thermodynamics and other stuff that things actually extract and construct, right? With temperature, so also the geometry change, but in the more simple way, yes, it's change in a linear fashion, okay?
I again.
I is the current, okay? It's how much charge I have that go through 1 second, okay? How many charges, numbers divided by 1 second, 1 second. Clear the concept? Okay, good. So we got everything we need. The ampermeter gives us this thing. The voltage is the battery that we use. Let's call it VB, V battery that we buy to measure it, right? And now we just found a term that actually holds everything inside. So this is R. R we know it to be rho L pi A squared multiplied by 6. We know the current from the ampermeter. Okay, we talked about the ampermeter as a selector in a party. You just count how many charges pass in 1 second, and we know the voltage of the battery, right? So we can extract L. The length of the tower gonna be VB divided by R multiplied by pi A squared 6 divided by rho 0. Okay, so and actually electricity is a really good method to measure the length of stuff. Okay, if they are electrical, right? Conduct some electricity. Perfect. The second thing I want to talk about is that you know that let's go that way. Okay, let's clean this. The second thing I want to talk about is actually concept that called current density. Okay, because think about it, that I is actually a really general term. Okay, it's like what is this is I, is a scalar. What is the I that go through this coin? But who said that the same positive charge that go in that direction didn't go twice in the middle for some reason? For example, think about corrosia. Okay, think about that the other part here is actually a little bit rusted, and electricity doesn't flow there really well. So most of the charge going to go inside the middle. So there's a bigger concept to I, which you're going to use a lot in the next chapters, which is the charge density. Sorry, not the charge density, the current density. It's actually really similar to charge density. Remember this term? That if we talk about charge, we had this thing, right? So the same concept we're going to have about current. We're going to have this thing. Okay? What does it mean? This is the charge, the current density, which means how much how much amperes they have in this specific place. Let's clean it. No, let's do it in a new drawing. So if I have this area, right, this coin, so how much actually penetrate this specific thing? Only this meter square, right? Multiply by its length, sum it on all the coin, you're gonna get the current. Okay? It's really similar to that concept. The only difference is vectors. Okay? Another way to think about it, I have to think about it as force equal integral P dot dA. I know that some of you learn solids too, right? So if I do, for example, a handstand, okay, imagine me doing a handstand. So who said that the force that I have here in the middle is exactly the force that I have here in the middle, in the pinky, right? So I can actually play with the force to balance me, okay? So the same concept here. Okay, same concept here. The pressure on each location on my finger multiplied by this specific area will generate a small force, right, dF, which gonna sum up to be the total force. Here, this small contribution gonna give us some contribution to the current, which gonna sum up to the total current, total amount of charges that go through this area. Clear? Concept is clear? Nice. Okay, so in our case, and most of the times we're gonna see this thing, not in the homework, yeah, but in exam it's more abundant. This word. I'm gonna tell you that the surface of the coin is unified. There's no reason for charge to go to some particular place than other, so we can actually simplify the current density. The question was, what is the current density? What is J? Question mark, right? So I can say that I equal to the current density, and the current density is a constant because there's no reason to go to other direction in the coin, right? So it can go outside of the integral. This is A, and we know A. What is A? The size of the coin, pi A squared. So J in our case is just I divided by pi A squared, because here we had I. Yes? This is clear? Okay. So, and we know I, right? We can extract it from here. We can use this term, and it's gonna end up to be 6 times the voltage of the battery divided by the resistivity divided by the length of the tower. Okay? See that if the tower is really long, less current, right? More things that resist it. Infinity long, no current at all, right? Good. Okay, the last part of this question is, you know, when you're talking about energy, okay, it's like camera 2 here. So when we talked about energy or money, I think money and energy are the same concept, right? So it doesn't matter to talk about magnitude alone, right? For example, Bill Gates makes $17. Doesn't make any sense. But if I'm going to tell you Bill Gates makes $17 per second, you're going to say, fuck. Until the end of the sentence, it just did money, a lot of money, right? Till the end of the class, it did a bunch of money. 1 day, 1 year, it's crazy. So we need to understand when we're talking about energy, about how much energy actually being used in specific second, okay? So the concept I'm going to talk to you right now is what is the power of the tower. What do I mean by that? Think about it when you had the feeling when you touched the phone and the phone was really hot, or some electrical device that get really hot. So when you use electricity, some of the energy got transient to the environment by the form of heat, okay? And that's what resistors actually do, okay? A resistor of lamp, here I have lamp of a car. You can see the resistors, there's 2 resistors inside which actually produce the light, okay? They change the energy to light to heat, okay? You can pass it to the student. Here it is. And it looks like a solenoid, the resistor there. And they actually plan the resistor in the lamp of the light to not work after approximately 1 year, 2 years. They actually design it that way. Okay? So what is the power of the tower? So power we denote by P, power, okay? And what we just said power is how much energy I consume per second, which means how much energy I consume per second, right? Okay? So how we define U? We talked about that in electricity we don't much care about energy. We care about voltage. How I can shift to voltage? Exactly. So this term is dt q multiplied by v. And in our specific case, the voltage is always the same. What is the voltage? The voltage of the battery, right? So this is a constant and can go outside of the derivation. So we have here VB multiplied by, and be careful, what did I just wrote here? What is this? Exactly. How much charge, the difference in charge, D is from the word difference, right? Difference in charge versus difference in time. Okay? This is exactly current. And the way for me to remember it is this formula, which, do you know the formula of the power? Yeah, the power is V. Okay, that's how I remember it, okay? So this is really important. In our case, we know the formula, right? In our specific case, VB is given. We just found the voltage to be pi A squared 6 multiplied by L rho. And this is how much heat actually this send to the room. And if you think about it about lamp actually give 100 joules per second. Each time you touch a bulb of light, whoa, this is really hot, 100 joules per second. And the human body is the same. Right now, each one of you heat the room by 100 joules each second. The reason the lamp is so hot and you're not that hot is because you have a more surface to do it. The lamp is really condensed, a really small area. Okay, clear? Good. So we finished the first question, okay? And we're going to move to another question, okay? Let's clean the board. Okay, so the second question gonna be about the telescope, okay? So we have a telescope. This is you watching the telescope, let's say. Here it is. Oh. And this is the telescope. And the telescope have this opening state, right? And also have the compact state, right? The compact state is when all the telescope is actually packed up in this manner, right? A lot of all these cylinders actually inside each other, right? And you know that this last one is actually size A, okay? And you know the resistivity of each cylinder. Each cylinder with radius R equal to resistivity constant multiplied by the ratio R over A. Okay, we know that. And the first thing I want to ask you, imagine that we have a lot of cylinders, okay? Really a lot of cylinders. For each radius, I can find you a cylinder, okay? So the first thing I want to ask you is, if I'm going to connect it in this way, here it is. Here I'm going to put some theta, here it is. Some plate, conductive plate, that's going to touch all the cylinders at once. Okay, so what is the resistance of just one cylinder? Okay, what is the resistance of one cylinder? So what is the formula for resistance? Do you remember? R equal to smiley face. That's how I remember it. Right, smiley face. Do this line here, A rho L, my method, and we're talking about just a small cylinder, one cylinder, so we're actually talking about dr, right? So right, we need to understand each component. These have a length of L, so what are the contributors that we have here? What is rho of each cylinder? Given, okay? So this is rho R divided by A. What is L of each cylinder? What? L. You see that if this is a cylinder, right? And the current go through the cylinder, the distance that the current need to go is actually all the cylinder. Do you see it?
Yeah, but didn't we say that the cylinders are...
It's small, not short. It's small in what? In thickness, in the R property. I said for each R we're going to find a cylinder, okay? But you bring me to the next question. What is, and I think the hardest one, what is the effective area of each cylinder? Okay? If you're going to see that, let's change the orientation to this one. So this is actually what? Small unit of area dA, which equal to what? If this is radius R, exactly, R d theta, but this is just one line. You told me how much is the base. What is the height? Is this, right? dr. Agree? Right? And if you're going to do the integral, this is going to end up to be 2 pi r, which means the whole thing extended by dr. So this is going to be 2 pi r multiplied by dr. Is this clear? Is this clear? Yeah? Okay. Perfect. So this is the resistance of every little cylinder. Okay. The second question, like we had before, is in what way all the cylinders are connected. in parallel or in series. So in what manner? In what manner the cylinders, or we can say resistors are connected. So let's think about it. This is the battery. So first of all, the battery connected to the big resistor, the one with the radius A. Okay? So connected to the one with the radius A, and then the cylinder is actually, can you put this camera in the middle? Like that I can hold these two? Yes, perfect. So the first resistor, the big one, R equal A, let's say, is, let's do current in red. So the current is coming, here's the current, right? And it's touching this cylinder and then reach the battery, right? So the outer one is actually touching the battery, you see it? What's going on if I'm going to a smaller cylinder from this plate? I'm touching, let's say, this cylinder. I'm going through the cylinder, the inner one, and then touch the battery. You see it? So I actually can draw it this way. I'm touching the battery, right? This is like the pita, the plate that we have here. This one. So all the resistors actually touching until the last one, right? So this method is actually parallel. Why parallel? Because all of them share the same voltage. Everybody enjoy the two terminals of the battery. This is clear? Yes? Okay. So I'm going to this part of the board. So right now, if we know how the resistor connected, what's going to be my next question? What is, yes, the equivalent resistor, or I like to call it what is our total, the total one, the one that's going to give the same result to the circuit. So our total in parallel is actually looking like this, which is the opposite of capacitors, right? The opposite way. This is for parallel, right? Good. So in our case, we have dr, right? We have this, so we're gonna use integral, and the term for dr is the flip one of what we wrote over there. And I want you to notice something really cool. Go here. It's not always gonna be that case. It's only happened in this particular question, but note what happened. What happened to the resistance? It's not depending on which cylinder I choose. It's rho divided by 2 pi a dr multiplied by L. Each resistor have the same resistance, okay? Just happen by luck. Why so? Because of this term. Because it was linear and the area was extended linearly, they cancel each other out, okay? But this is not gonna be the case. I just did that in a purpose to make the question more easy for us. Let's go back to here. So what we have here is 2 pi a dr divided by rho 0L. I just gonna remind you that I do the one opposite and I need to do the one opposite. What is the boundary of the integrals? These are the boundaries of the integral. We're going to start from 0 till the last radius that we have, which is a, right? And this is a constant, right? It just multiplied by a. So the result is a rho L divided by 2 pi a squared, right? Yes, that's what I got. Okay, cool. And now I'm going to give you a hint. I want to measure what is, if I know the battery, what is the current that I have. What should I do? What equation I'm going to use? If I want to find, let's clean, I'm going here. I want to leave it. I'm going to clean this. If I want, I have the resistance. I have the voltage of the battery, and what I want to know is the current. What I'm going to use?
V equals I.
Exactly, V law, or the more formal name, Ohm's law. Okay? Ohms are actually the units of resistance. Okay? Ohm. And this is called Ohm's law. Cool? Or the Veer law, the Beer law. Okay? Cool. So we can find I just by dividing V by R. This is given. And this is this term. 2 pi A square rho 0 L. Okay? Good. We found the current. If I want to find the power, how much heat all these cylinders actually propagate to space, what I'm going to use, which formula? What is the formula for the power? A camera to here. Formula for the power is P equal V. V multiplied by I, and we just know that V is the voltage of the battery. We know that I is the current, right? This current, 2 pi A square rho, right? And we have here VB squared, because we have one from here and one from the current itself. Okay? Cool? Great. Last question I want to ask you is, what is the current density in each cylinder? Let's say what's the current and what also the current density. Okay? So I'm going back here. So let's see what's happening. Okay? So we can find what is the current if we know the resistors, right? Because we have Ohm's law. Ohm's law said that if you know the voltage, you can find the current given the resistance. And I want to know what is the current for each resistor, okay, dr, okay? And we know the resistance of each resistor. We know it to be dr, right? Which is a constant. It's rho L. We found it in the first section, 2 pi A dr, right? So I can actually know that, and all the resistors share the same voltage, right? Right, because they connect in parallel, which means each resistor feel I am the king. I have all the voltage, right? I don't need to share it. So in each cylinder, we see that we have the same current, VB divided by this constant, right? 0L 2 pi A multiplied by dr. But I wanted to know what is actually the current density. What is the formula for current density? It's like I, but instead of talking about the general I, it's talking about what's happened to the current in each place in space, right? In our case, it's each place in R and theta, right? Because when I go through cylinder, I have where I am, which cylinder I am, R, and which theta I have, which angle, right? dA. Right? This is the thing that we want to solve. Right? So note for something really interesting. Okay, I'm going to tell you that there's not any preference to the current density to go in each direction. Okay? For the current density, it's the same. And what you're going to see, it's going to see the J, if it's a constant. יש לכם שיעור פה?
כן,
וחצי, יש לי עוד 5 דקות. בסדר? תודה. Okay? So J node is actually multiplied by the integral. And no, this is for specific cylinder, for specific dr. Okay? That's what we are zooming into. Okay? So what is this size? This area is actually the area of a specific cylinder. This area that the current needs to go through. You see it? Which is different from, example, this thing, this one. Okay? If some of you need to go because you have another class, it's okay. Because we started a little bit later, I'm gonna give extra 2 minutes just to finish this. Okay? So you see that the area are different, but what is the area? We calculated before. Is equal to, this is JF, a J node, and this area is a dr, which how much thick this, and 2 pi r. 2 pi r. You see? And what you're going to notice here, that if this is constant, and this is changing in r, we're going to say that J node here, J node is actually changing from each cylinder. There's some cylinders, there's a uj, J as a function of r, is actually this term, I dr, divided by the specific area of each dr, which is changing, right? It's I dr divided by this term, dr 2 pi r. That's what I want you to notice, okay? Which means in the really small cylinder, you have a huge amount of core density, okay? And the top one, the last one, you're gonna have less. Okay, the last thing I want to talk about is congratulations. You finish half of all the material for the exam. Right now we're going to start a new subject which is called magnetism, because we're going to learn that electricity alone is not working. Something else which is called magnetism actually really connected to it, and that's the reason the class is called electromagnetism. It's one word, it's not two words. They're actually the same phenomena in different view of observation, and I want to say to you that you didn't finish 50% of the class. You actually finish more, because all what you're going to see right now in magnetism going to be the same as we saw in electricity. We're going to have a really similar properties, but you're going to be more experienced because you have the previous background of electricity, and the class from now on going to be really easy for you guys, okay? So with this said, I'm going to see you next week. Congratulations. Enjoy the Independent Day. Yes, and see you later. And I have here some resistors if you want to see. Small resistors.